In this lecture, we're going to go over three main types of learning problems that machine learning and deep learning models solve. And these are supervised, unsupervised, and reinforcement learning. The difference between these three types of learning problems is not the type of input data that they can process. All three types of models can process any type of input data in any domain. They can all take images, sound, words, etc. Instead, the difference between these types of models is in the nature of their training data and what information they have about their training examples while they're learning. Because the information in the training data differs, supervised, unsupervised, and reinforcement learning models will take different approaches to learning about the data. So while both traditional machine learning and deep learning can be used to solve supervised, unsupervised, and reinforcement learning problems, the use of deep neural networks has created great advancements for all three types of problems. The first type of learning problem is supervised learning. This is the kind of learning problem that's the most used in current industry applications. Here, the model is given a training data set where each example in the training data set has a label. This label is typically either a category or a continuous number. When the label is a category, the goal of the model is to predict the category membership of its input data, and this is a task known as classification. If the label is a continuous number, the goal of the model is to predict this number, and this task is known as regression. Let's look at an example of supervised learning. Here are some pictures of cats and dogs, each labeled with whether it is a cat or a dog. A supervised learning model would be trained on this data to classify an image as being a cat or a dog. So the training data will be many labeled images of cats and dogs, and the goal of the model will be to predict, given an image, whether it is a cat or a dog. The task of deciding what category something belongs to is known as classification. Here, our example has two categories, cats and dogs, but in general, we can have multi-class classification, which means there are going to be more than two categories. As an alternative to having our model output just an all-or-nothing prediction for whether something belongs to a category, we can also have the model output a probability of something belonging to a category. So here, the model can communicate the uncertainty for images that are a bit more ambiguous in terms of their category membership. For example, it could output the probability of 0.5 for this half-cat, half-dog-like thing that's shown on the bottom right. Another thing is that the model will only be as good as its training data, and this is true for all types of learning models. And so if the model was only trained on pictures of real dogs, and then it was asked what it thought of this picture of Snoopy, it's probably not going to predict that Snoopy is likely to be a dog. For anything we'd like the model to predict, we just have to have an appropriately labeled data set. So for example, imagine we're opening an online pet shop for cats and dogs, and we want to know how much pets should cost based on their image. So now we'd have all our photos labeled with how much this cat or dog should cost in the pet shop. And then we train our model to predict the price of an animal given its image. In general, the task of having models predict continuous values is known as regression. There are many things that our models can learn to predict. As long as we have a suitably labeled training data set, our models can learn to predict these labels. And I want to emphasize that the hallmark of a supervised learning problem is not the type of data that it processes. Instead, it's the fact that every single data example in your training set has a label. And what constitutes a single data example is whatever you define it to be. So let's say maybe you want to classify dance moves. And so a single data example would be a video stream of dance movements. Or if you wanted to classify tweets, a single data example would be a bunch of words. Or if you wanted to predict what someone's going to purchase next, a single data example could be a sequence of their previous purchases. As long as for your training set, for whatever you define a single data example to be, that every single data example has a label, then you can do supervised learning. As is the case for all three types of learning problems, both traditional machine learning and deep learning can be used to solve supervised learning problems. There are times when deep learning does not offer any advantages over traditional machine learning. This is the case when we don't have much data, or the number of features that we need to represent our input data is relatively small. However, for extracting information from complex environments, where we have large amounts of labeled data, deep learning offers huge advantages over traditional machine learning. One domain where deep learning has been absolutely killing it is in computer vision. One of the key breakthroughs in deep learning came from a supervised learning model for image recognition. There's a machine learning competition called ImageNet. ImageNet is one of the most prominent computer vision competitions, and it's an image classification task, which means we want models to predict a category for each image. ImageNet has a training data set of over 1 million images, hand-labeled by researchers into 1,000 categories. These categories are very fine-grained. So for example, there are 120 categories for different breeds of dogs. One difficulty in image classification is that images from the same category can look very different. For example, take these images of fruit. It wouldn't be easy to describe what visual features made both of these images images of fruit. Also see how different these two images that are classified in the category pool look. Again, there's no obvious way to describe what visual features make both of these images belonging to the category pool. So for a problem like image classification, where it's very difficult to explicitly define what features are relevant, the ability of deep learning models to automatically discover relevant features that we don't have to explicitly define offers huge advantages. One of the major deep learning breakthroughs was the supervised learning model called AlexNet. AlexNet used a type of deep learning known as a convolution neural net, and when trained on the ImageNet dataset, it had an error rate reduced by 50% compared to the previous best performing model. This was a huge improvement compared to the much more incremental improvements that you typically see when a new machine learning model is introduced. Jeffrey Hinton, who is one of the world's leading researchers in deep learning, submitted the AlexNet model to NIPS, which is the world-leading deep learning conference, in 2012. This paper had been cited over 30,000 times, and it was one of the critical publications that jump-started the deep learning revolution. Since then, deep convolution neural nets, which are models like AlexNet, have become the standard for image recognition tasks. By 2015, deep learning models were reporting better than human-level performance on the ImageNet task. Here are some examples of images that a model could classify correctly. It could tell that these were horse carts, that these were forklifts, that this was a birdhouse, that this was a kukul, this is a commandor, and that this plant is a yellow lady's slipper. I don't even know what these things are, so definitely better than I could have done on these images. This labeled data set of 1 million images offered by ImageNet gave a huge boost to computer vision models for all types of image processing tasks. And this is through the concepts of pre-training. The idea of pre-training neural networks is a very powerful technique for the situation where we have a specific problem we want our model to solve, but we don't have enough labeled training data for our specific problem for our model to learn the solution from scratch. For example, let's imagine we want to build a very specialized plant species detector. There are some plant images labeled on ImageNet, but let's say we want to build something so fine-grained and specialized that a botanist could use. There aren't labeled data sets with millions of examples for all the different species of plants. Instead, we have something more like 7,000 labeled examples of 60 different types of foliage. 7,000 examples for 60 categories is usually not enough to train an image recognition model from scratch. So the way we handle this is with pre-training. What pre-training means is that we train a model to solve a more general problem that we do have the data for, before fine-tuning our neural network to specialize for our more specific problem, for which we only have a smaller labeled dataset. Training a model on an existing larger but less specialized dataset first allows the models to find basic feature representations that can then be fine-tuned for our specific problem. By training on this larger, more general dataset, we come up with an efficient feature set that serves as a starting point that we can use for our second model that we want to solve a more specific problem, such as distinguishing between 60 different types of foliages. We can now solve our more specific problem with much fewer training examples because our model has been given a jump start in finding the efficient feature representations that it needs to solve the problem.